Atomic units form a system of natural units which is especially convenient for atomic physics calculations. There are two different kinds of atomic units, Hartree atomic units and Rydberg atomic units, which differ in the choice of the unit of mass and charge. This article deals with Hartree atomic units, where the numerical values of the following four fundamental physical constants are all unity by definition: electron mass, elementary charge, reduced Planck's constant, Coulomb's constant. In Hartree units, the speed of light is approximately. Atomic units are often abbreviated A, U, or O, not to be confused with the same abbreviation used also for astronomical units, arbitrary units, and absorbance units in different contexts. Use and notation. Atomic units, like SI units, have a unit of mass, a unit of length, and so on. However, the use and notation is somewhat different from SI. Suppose a particle with a mass of m has 3.4 times the mass of electron. The value of m can be written in three ways. This is the clearest notation, where the atomic unit is included explicitly as a symbol. This notation is ambiguous. Here, it means that the mass m is 3.4 times the atomic unit of mass. But if a length L were 3.4 times the atomic unit of length, the equation would look the same. The dimension needs to be inferred from context. This notation is similar to the previous one, and has the same dimensional ambiguity. It comes from formally setting the atomic units to 1, in this case, so, fundamental atomic units. These four fundamental constants form the basis of the atomic units. Therefore, their numerical values in the atomic units are unity by definition. Related physical constants. Dimensionless physical constants retain their values in any system of units. Of particular importance is the fine structure constant. This immediately gives the value of the speed of light, expressed in atomic units. Derived atomic units. Below are given a few derived units. Some of them have proper names and symbols assigned, as indicated in the table. Kb is the Boltzmann constant. SI and Gaussian CGS variants, and magnetism-related units. There are two common variants of atomic units, one where they are used in conjunction with SI units for electromagnetism, and one where they are used with Gaussian CGS units. Although the units written above are the same either way, the units related to magnetism are not. In the SI system, the atomic unit for magnetic field is 1 AU equals 700523500000000000000 2.35 times 105 TE equals 70092350000000000 2.35 times 109 G, and in the Gaussian CGS unit system, the atomic unit for magnetic field is 1 AU equals 7003172000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000 1.72 times 107 G. Other magnetism-related quantities are also different in the two systems. An important example is the Bohr magneton. In SI-based atomic units, AU, and in Gaussian-based atomic units, AU. Bohr model in atomic units. Atomic units are chosen to reflect the properties of electrons in atoms. This is particularly clear from the classical Bohr model of the hydrogen atom in its ground state. The ground state electron orbiting the hydrogen nucleus has orbital velocity equals 1, orbital radius equals 1, angular momentum equals 1, orbital period equals 2 pi, ionization energy equals 1/2, electric field equals 1, electrical attractive force equals 1. Non-relativistic quantum mechanics in atomic units. The Schrödinger equation for an electron in SI units is the same equation in O is. For the special case of the electron around a hydrogen atom, the Hamiltonian in SI units is while atomic units transform the preceding equation into comparison with Planck units. Both Planck units and O are derived from certain fundamental properties of the physical world, and are free of anthropocentric considerations. It should be kept in mind that O were designed for atomic scale calculations in the present-day universe, while Planck units are more suitable for quantum gravity and early universe cosmology. Both O and Planck units normalize the reduced Planck constant. Beyond this, Planck units normalize to 1. The two fundamental constants are general relativity and cosmology, the gravitational constant g and the speed of light in a vacuum. The orbital velocity of an electron around a small atom is of the order of 1 in atomic units. So the discrepancy between the velocity units in the two systems reflects the fact that electrons orbit small atoms much slower than the speed of light. There are much larger discrepancies in some other units. For example, the unit of mass in atomic units is the mass of an electron, while the unit of mass in Planck units is the Planck mass. A mass so large that if a single particle had that much mass it might collapse into a black hole. Indeed, the Planck unit of mass is 22 orders of magnitude larger than the O unit of mass. Similarly, there are many orders of magnitude separating the Planck units of energy and length from the corresponding atomic units.